G'day further math students. In this video we're going to go through how you can fit a trend line to a time series plot or to time series data, and also this process of forecasting. Even though we're using some different language here, this is really just exactly the same thing as what we did in scatter plots, where we determined the equations of least squares regression lines and use them to make predictions. The word forecasting is just used when we make prediction with time series data into the future. Okay, so you hear things like the weather forecast. That's when people predict the weather for tomorrow or the next week or something like that. So forecasting just means to make a prediction into the future. And really, everything else is the same in terms of what we used to do with scatter plots when we did least squares regression lines. And you're going to kind of hopefully see as we go through a couple of examples that those skills will be very repetitive from what we were doing in our, I think it was chapter 4 work. So one extra thing to note here, just when we forecast, by its nature, it means we're extrapolating, because we're typically predicting into the future where we haven't actually got any data yet. So it's important to note that forecasting is a process of extrapolation, and the further into the future you predict, the less reliable that would become. And you might get questions about that because, as I said, it is a form of extrapolation. Okay, let's get stuck into the first example. Our data in this question is the number of enrolments at Melbourne University, which has been recorded at 5-year intervals and shown in the table below. This is a little bit of a tricky one. We're going to put this data into our calculator. Normally, or not normally, but a lot of the time with time series data, we often just start from the number 1. So the first time period is just 1, and we put the numbers in as like 1, 2, 3, 4, 5. So if it was days of the week, like Monday, Tuesday, Wednesday, you would just put that into your calculator as 1, 2, 3, and so on. When it's the year number though, because years are actually numbers, you can put the year numbers into your data, and particularly, into your calculator. And particularly in this question where it goes up in lots of 5 years, it would be kind of awkward to number this as 1, 2, 3. So we're actually going to put these numbers in as the year number into our calculator. Time is always the explanatory variable, so this is going to go into list 1. And the number of enrolments is our response variable, so that's going to go into list 2. So I'm just going to show you quickly how that'll look on the calculator here. So we're going to go into our statistics screen. We're going to put in the years in list 1. So it was 1995, 2000, 2005, 2010, and 2015. Right, and our Y values, our response variable values, enrolments 32150, 35871. So this process is always a little bit tedious, but it is obviously very important to get this right. So as much as you're tempted to rush this when it's a SAC or an exam, you're better off taking an extra few seconds and making sure the numbers are in there accurately and doing a quick double check, because it only takes one wrong number to muck up all your values. All right, once we've got the data in there, our process here is calc, regression, and then linear reg. It's not a situation where we're transforming any data or anything like that, so we don't have to worry about any other list other than what's in list 1 and list 2. We hit OK, and we get our equation in the form y equals a plus bx. So they've given us the value of a and the value of b here. Our job is just to write this down in terms of the variables. So remember that y is the year. Y is the enrolments, and x is the year. So the least squares regression equation was, in terms of just y and x, it was y equals a, and a was, I should probably put this back here, a was -1, oh, let's just write it down, -1, sorry, it's hard for me to put this on the, get both screens in one here on this little video, that might be better. Y equals -1713899 plus b, so plus 875. Now it's 0.02, but the question said to 1 decimal place, so it's actually 0.0 times x. Okay, but we know that y and x actually have names here. Y is enrolments, and x was the year. Okay, so obviously you really only need to write that second equation down. That one's just to show what was on the calculator screen, and this is putting it into context. Okay, part B of the question, to the nearest whole number, in what year are Melbourne University's enrolments expected to first reach 6,000? So this is kind of asking us to make a prediction or you do some forecasting. This is saying we're interested in enrolments equaling 60,000. We want to know when that would happen. So making a prediction just means you take your equation and you put a number in and work out what the other number is going to be. So if we put enrolment equals 60,000, well, what we can do is we can solve for the year, right? So depending on how many marks the question's worth, you might need to write this line as a working out step if it was a 2-mark question. But what we're going to do from here is just pop this into our calculator and solve for year. And we're probably just going to use X as year. So I'm going to jump into the main screen. And we're just going to use Action Advanced Solve was 60,000 times X. Remember, if you're solving for X, you don't have to do anything extra to the end of the equation because your calculator will by default always try to solve for X. I've got the calculator in standard mode. That's not really a useful answer in terms of what year that's going to be. So if I pop that into decimal mode and just redo the calculation, all right, 2027.3. So we get year equals 2027. Well, 0.3 is not much good to us, so it's just going to occur during 2023. Okay, so and it does say in the question to the nearest whole number as well, just to emphasize that. And so what this is saying, or what this is predicting, is that it'll take until year 2027, and in year 2027, that's when the enrollments will first reach 60,000. I've also just realized I made a spelling error there, and that's annoying me, so I'm going to fix that. 1L in enrollment. So in this second example of fitting trend lines and forecasting, we're shown a question where we have deseasonalized sale figures. So these values have been deseasonalized for Petra's shop. So no, not really any context there. Petra's obviously some person who owns a shop. And this time we've got quarterly data across 3 years. So you can see that we've got 2016, 2017, 2018, and 4 quarters for each of those years. So our time period here is the quarters. That's going to be our X value. You can see if we're going to try to put this into our calculator and come up with a regression line, which is what the first question is asking us to do, well, we're not going to be able to put in the numbers 1, 2, 3, 4, then 1, 2, 3, 4 again. So this is a question where we actually have to take the first time period and just call it 1, which I guess it already is. But as we go through the data, the next quarter, so the first quarter of 2017, we're just going to put that in as time period 5, right? And then 6, 7, 8, 9, 10, 11, and 12. So we've actually got 12 quarters here, and those will go into list 1. Those are our explanatory variable values. Our response variable, or our Y values, are the deseasonalized sale figures, which will go into list 2 of the calculator. Now, given that we've already done one example a bit similar to this, I strongly encourage you to pause the video and have a go at working through the question on your calculator on your own, and then kind of watch the rest of the video and see how you went. Just to save a little bit of time, I've put this data into my calculator already, which I'll show you here. And so I guess because the first question is asking us to find the regression line, let's take care of that first. So we've got our data into list 1, and you can see that we've just numbered, because we had 12 quarters of data, we've numbered list 1 as just 1 through 12. And the sales figures, the deseasonalized sales, have gone into list 2. We're then going to do our calc, regression, and linear reg. We've put the X values in list 1, Y values in list 2. We don't need to change anything here. And we hit OK. So this is giving us an A value of 837.98. Now let's check this question again. The question said, it's one of those fill in the blanks ones, and it says to calculate the equation, round values to 3 significant figures. Okay, so our value of A is 837.9. So if we're rounding that off, the third significant figures, that's 7, but the 9 after that's telling us to round off. So this is going to be 838 to 3 significant figures. And the B value, our gradient value, is 32.06. So that 0 there is the third significant figure. The 6 afterwards tells us to round up, so it's 32.1. All right. So we've got our values in the equation now filled in. Next thing says complete the following statement. The regression equation predicts that on average the deseasonalized number of sales increase by something each quarter. So that's kind of like saying, like, every time the quarter number increases, the deseasonalized number of sales increases by something. Hopefully that statement, even though it's got a part of it missing, is ringing bells as our gradient interpretation, because really that's what that's doing. That's interpreting the gradient, and the gradient is 32.1, right? The gradient's the number that's multiplying the X variable. And so The number that goes in here is 32.1 because that gradient means that every time the quarter number increases by 1, the sales are going up, because there's a positive gradient, by 32.1. Okay, and part C, the seasonal index for quarter 3 is 0.997. Find the number of actual sales forecasted for 2019 quarter 3. All right, so there's a little bit going on here. Remember that in our original data, all these sales figures were deseasonalized, right? So when it's saying to find the actual sales, that word actual is going to be important. We've got a seasonal index, which will help us to convert from the deseasonalized values to the actual values. But before we get to that, we need to think about, well, how can I get a prediction for 2019 quarter 3? Now, if our quarters have gone up to 12 so far, so 2018 quarter 1, 2, 3, 4, where actually our time periods 9, 10, 11, and 12, well, 2019 quarter 1, quarter 2, quarter 3, quarter 4, if we were continuing our counting, this would be 13, this would be 14, and quarter 3, which we're interested in, would be 15, right? Quarter 3 of 2019 would be the 15th quarter overall. So this would be quarter number 15, right? And that's the value that we're going to have to substitute into our equation to start things off, right? So we're going to say, using the equation, the deseasonalized sales would equal, so I'm just using the equation here, 838 plus 32.1 times 15. Oops. So let's calculate that. Getting out of the stats screen and into the main screen. Times 15. So we get 1319.5. I'm not going to round that off because I'm going to try not to round anything off until the very end. So that's the predicted deseasonalized sales, right? But remember that we asked for the number of actual sales forecasted for this time period. So we're going to go back to one of our rules from seasonal indices in 6D that says that the actual, I guess, value, if we think generally, the actual value equals the deseasonalized value times the seasonal index. Okay, so if you're, I guess, because it's a bit backwards, right? So when we given a deseasonalized value and we want to find the actual value, we're going to multiply by the seasonal index. That's a rearrangement of one of our other formulas, okay, when we're working backwards to find this actual value. So for this question, that's going to be 1319.5 times by the seasonal index, which was given to us in the question, which was 0.997. And that will equal, just going to take this, multiply the answer by 0.997. That's going to give me 1315.54. Well, 0.5415 to be really precise. The question's probably not well written, and I apologize for that. It should probably tell us whether to round to the nearest whole number or not. Look, let's assume that it did, because it should have, because all the other sales figures were given as whole numbers. So let's say that it's 1316 to the nearest whole number. But I hope the idea there makes sense. So this was a tricky question. We had to do two things. We had to make a prediction using the regression equation, but then because this was a deseasonalized prediction or a deseasonalized forecast value, to get the actual value, we've had to apply this formula here that we used in 6D.